Today we get to finish up sound. We'll transition into light after today. But it's still waves, same type of properties, wavelengths and frequencies and periods. We'll just start seeing things more than hearing things. Do you guys have any questions about things as you've been going over the homework and anything that's bugging you? Okay. At least want to ask periodically. You can always raise your hand and ask if I don't ask. But all right, then friendly reminder, I've received one paper thus far. The last day to turn those in is Friday. The last day to turn in your paper. You've had all semester, and the last day is Friday to turn your paper in. Yes? Both. The instructions say both. It's right there in the rubric and online in the WebAssign. Yeah, you submit it digitally and a hard copy.
Is it digitally through WebAssign or digitally through Canvas?
WebAssign, that's where the assignment's at. The easiest is just upload it right there. If you can't get that to work, you can email it to me. If you can't get that to work, you can bring in a USB stick. Yes, hard copy and digital copy as the assignment has listed all semester. Both. Any other questions about the paper? All right. You will have a homework due this weekend. It covers chapters 19 and 20, the sound stuff. 19 was starting vibrations and waves in general, and 20 is about sound. And that'll be due Sunday night. We will start chapter 26 Friday, but you won't be. You don't have to worry about homework on that yet because we won't have finished it. But you'll have access to it by then. We're getting down to the wire. It's getting close. Another friendly reminder. I have sent out, it's been a while several weeks since I sent the last one out, but I've sent multiple emails about unassigned clicker device ID numbers. For example, there's somebody that has participated in clickers the last 5 times we've done it, but it's still an unassigned device. So I know somebody is still coming to class and not getting credit. But I've never heard from you, so you won't get any credit until you reply or fix that. So, yeah, there you go. Those of you that can see your clicker grades on Canvas, you know it's working. If you have a flat 0, and you've been responding and coming to class, well, maybe there's a big tip-off that you haven't done something. Been trying to warn you, but you can check on that. Let's see, other logistics stuff. I can't think of any. Okay, one of my favorite things to do with sound is predict how far away the storm is. You guys know that little trick? You hear the thunder, and then you count. What do you count to? What have you heard? Yeah, I know how to count. What do you do with that?
Each second is a mile?
Each second is a mile? That's about right. Yeah, absolutely. I guess it's close enough here in the United States. One second's actually a little closer to a kilometer, but whatever, it gets us there. Because, you know, you can see it. Light travels faster. It travels 3 times 10 to the 8th meters per second. Zippy. So sure, the light will reach us much quicker than the sound that travels 340 meters per second. So you have the time difference. Velocity is distance over time. That's the same thing as wavelength times the frequency. So yeah, if you want to know how far away it is, you can still go back to how we did it before. I know, somebody won't be able to see always. Does this help any or make it worse? No comment. Okay. 340 meters per second, we'll say, you know, the speed of sound at room temperature. It's probably a little cooler in a rainstorm, but not always. Yeah, and if it takes 1 second, I said something wrong. I'm wrong. 3 seconds is closer to a kilometer than 1 second is to a mile. That's what I meant. Whatever. Let's do the 3 seconds. That'll work out nicer. That comes out to be 10, 20 meters, about 1,000 meters, so that's about a kilometer. If somebody wants to convert, 1 second is about 1 mile. So sure, you see the flash, 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000, 5, 1,000. You hear it. You know it's about 5 miles away. When do you start worrying? When do you guys personally worry?
If they're really close, like you see it and you hear it.
Yeah, if you see and hear it at the same time, yeah, you can take cover. But I even, if it's like a second or two, that's just a mile or two away. And if the storm is coming at you, you got a little warning to take cover. But this still works with waves. This is the speed of the wave, just like we did projectiles and objects before. So you can still do all that motion stuff and see how long it takes. If you have a wave, I think there's a homework question of like a submarine or a boat, I forget, and it sends a wave down. It bounces off the ocean floor and comes back up. Well, if you time how long it takes to do that, you send out the pulse and it comes back 3 seconds later. If you know the frequency you're using and the wavelength, you know how fast it travels. You know the distance to the ocean floor because it has to go down and back up twice that distance. That's how they can survey how deep the ocean floor is. Submarines can do it, sending out radar and things. It goes, reflects off another ship, and comes back. They time that, and they can figure out how far away it is. They can even, how many of you have gotten a speeding ticket? Yeah, you're not going to admit. How many got a speeding ticket, but you know it's because the police officer was using a radar gun? No, I didn't. The radar guns work that way. If I bounce it off you, it comes back, and I can get the time. That uses the Doppler effect. If you're moving away from me at a certain speed, which way will the frequency shift according to the Doppler effect? If you're moving away from me and I send out a source of sound, radar, and a wave, it bounces off you, comes back. It travels at a certain speed. It has a certain frequency. If you're moving away from me, how will it shift? Lower. Lower frequency. What happens to the wavelength? Longer. They get spread out. Because one will bounce off of you and come back at me. But then if he just moves further that way, the next wave front will take longer to get to me. They spread out. Longer waves, lower frequencies when you guys are going apart. If you're coming together, it'll be the reverse. And so the rate, the amount of that shift, of that Doppler shift, tells me how fast we're going apart or towards each other. I know. So if I'm fixed, then I know it's because of your motion, and I know how fast you're going. It uses the Doppler effect. We do the same thing with stars. The light from one side versus the other. If it's coming at you or towards you, and you can know how fast a star is rotating. All right. I have a few more clicker questions to help us understand this better. All right, same channel. You can see the session ID. If you were swift there, I was on the wrong slide and you saw the answer. Oops. We'll do it anyway. So in which of these materials does sound travel the fastest? We talked about the speed of sound traveling different in different materials. What's the key to the speed of sound? What makes it go faster? Thank you. I tried to say the word a lot. Interactions. So there's your clue. One of those is a gas, one is a liquid, one's a solid, or maybe they're all the same. Remember, sound is a mechanical wave. I can emphasize this. And it needs the medium to travel through it. It's got to interact with the medium and make it vibrate, which then bumps into its neighbors, makes them vibrate, and that's how it gets transmitted. If there's nothing to bump into, sound can't travel. Light, on the other hand, doesn't need anything. It'll propagate all on its own through empty space or a vacuum. It can go through transparent objects on its own. It will interact with them, and we'll discuss that, but it doesn't need the medium to do so. All right, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. The answer is indeed C, as most of you guessed. So, talk to me, those of you that didn't get steel. Be brave. What are you thinking? Don't be embarrassed. You don't have to, but I'm curious, what are you thinking so I can help? Because obviously some other people are also. Well, I did want to give you the opportunity. Okay. By show of nodding of heads, less conspicuous. Those of you that missed it, do you understand it now? Okay. Steel is a solid. The particles are more closely packed to each other, like the dominoes that were close. So they interact more often. There are more interactions. Thus, it can get through it more quickly. What would be second fastest? Water. And then the air. Okay. The speed of sound varies with which of these? If you change A, B, C, or D, which one of those will also change the speed of the sound? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. There's a spread. Most of you said all of them. Next was C. That's enough. We can reopen it. Talk to your neighbor. Discuss what you're thinking. Find somebody that has a different answer than you. Learn from each other. Give you another minute or so. It sounded like good discussion. Let's get your votes in now. Let's see if it's changed anything. And then we'll discuss the right answer. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, it's shifted. We got more on the C than we do the D. Get this out of the way. So we can read what this says first. Loudness varies with amplitude and pitch varies with frequency. Speed is not influenced by amplitude. That's just how loud it is. So same note, ah, ah. It's louder, but it didn't change the frequency. It didn't change the speed that it traveled to you either. Listen to this. Ah, ah. Did I change the frequency? Did I change the speed that sound travels to your ear? No, this is good, because if you were in listening to an orchestra, that would be really annoying. You'd hear the piccolos at a different time than you heard the tuba. Because they're different frequencies, if that changed the speed that they traveled through air, you'd hear them at different times. That'd be really annoying. Yes? So those of you who are thinking V equals F lambda or F wavelength, if you change the frequency, like piccolos versus a tuba, what also changes? What's different about the wave coming out of a piccolo than from a tuba? What's more? What? The frequency's higher on a piccolo.
But then the wavelength changes too?
So which one the wavelength changes? Which one's a smaller wave? The piccolo. That can adjust. But we didn't change the speed of sound in the air we're listening it to in that case. Now, we can think of another case, and that might be confusing you, so let's discuss it. The guitar. If I change the frequency that I play, but on the fixed string, how did we do that? In other words, an open string from the two bridges. You just pluck it. How do I change the frequency? I could tighten it or shorten it. Right, if I shorten it, then I haven't changed the string itself. I just made the wave smaller, so the frequency's higher. We just discussed that. If I tighten it, I haven't changed the wavelength, correct? But it'll sound higher pitched. Now you have changed the velocity because you've changed the medium that it's traveling through. It's now a different type of wire. It's a stretched wire. The molecules in there are arranged differently. So it's like you changed mediums. It was like going to a different string. So in that case, yes, you can change. If you change the frequency, you change the velocity. But in that case, it was because you changed the velocity, the frequency changed. Sound travels, a wave travels faster in a tighter string than it does in a loose string. Thus, the frequency changed. But I still like the analogy of, but they all travel to you at the exact same speed through the same medium. Does that help? Now, temperature does, because temperature would change the medium. Hot versus cold air. That would change. How many of you play an instrument? Why do you tune up at the beginning of a band or orchestra or symphony? What do they tell you to do, like with those wind instruments quite often? Yeah, the space could be different. And basically, it's the temperature of the air and or your instrument. Think about the air in a flute. You come out of the winter cold and you start blowing, and it'll sound different than once it warms up, because the speed of sound traveling up and down that column changes. And so you warm up to try to get it to equilibrium, and and match each other, of course. So you're all in the same key. I wanted one more. All right, go. Beats. That was me over there on the end last time with the tuning forks. And whether they were different frequencies or not. You hear that wah, 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 or wah, 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 wah. That's beats. What creates that? This will be our last one. How many of you are singers? Fancy yourself as singers. Is it hard to stand next to somebody else that's singing a note just a little bit off from you? That means you two are slightly different frequencies. If you can hold those without it throwing you off, you can hear beats, just like we did with the tuning forks. And it's hard sometimes. We want to match. It's dissonance when the frequencies are close but not right. That's chords sound good when they're far enough apart to match up. But if they're just a little off, yeah, they sound terrible together. Certain notes sound terrible together. Dissonance, we call it. But it's because you're hearing that beats. All right, most of you voted 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. 80% of you interference, that is correct. The waves are going in and out of phase. Superposition, they add up or subtract. They do both. When you hear it, it's loud, they're constructive interference. When they're opposite, it's destructive. It's both. That's interference. They're interfering with each other, going in and out of phase. Okay. I wanted to show you this one. Remember this was the Doppler effect, because you could hear it go. Now, if you just heard that, you might think it could be due to the Doppler effect, because you're kind of hearing a shift, but it's not. That's because, I mean the beats, for beats. But it's not. It's because it's the Doppler effect. But I wanted to point out to you, kind of as a review, why this works. It's pretty cool. If the top is moving faster than the bottom, what else is happening? And there's an air pressure difference due to Bernoulli's principle. Where's the pressure less? At the top. It's like the airplane wing going through. It's deflected. And so the air is going faster here. There's a corresponding drop in pressure. Higher pressure down here. That creates the airflow through this tube. Its length determines the wavelength, just like instruments do, like clarinets, and which hole you cover on a flute. The size of the wave. That's how you make the different notes. So that's the notes we get. If I change the speed, there's a corresponding drop in pressure, and the air actually can move faster or slower, the speed of the wave. That's why I can go. So let's see it. I got some paper bits here. I'm just going to hold them up underneath here, let the air still get in, and let's see if you can see it. They get pulled up. They actually get pushed up. The higher atmospheric pressure is pushing the air in. They get trapped in the airstream and go up it. Kind of cool. I have two rods here. Which one do you think is higher pitched? The shorter one. Oh, I have these in the wrong spot. Not this one. Let's see. If I hold the middle and whack them individually here. Short one. Longer one. It is a lower frequency. Higher frequency. You can picture a wave traveling up and down. It goes this way and reflects off the end and comes back. And then it sets up a standing wave. You can picture it like our slinky or the wave spring. And the size of the wave is determined again by the length. Hence, a longer wave will vibrate more slowly and have a lower frequency compared to a shorter. Again, because these are in the same material, so the speed of sound is the same in each of these. Look at it this way. If it's the same speed, it takes longer to get here and reflect back. It takes more time than it does here. This is fun too, because you can do the Doppler effect with this. Let's see. You hear it? Kind of shifting. That's Doppler effect too. All right, Tina, will you help me? This is called a space phone, and I'm really sad I can't find these online anymore. The big ones. They have the short ones, and they work. They're just not as cool. But to emphasize echoes, you can send a wave to it back and forth like we did. But my favorite is if you talk. Second favorite. Hello. Can you hear it? You can hear it bouncing back and forth. Waves reflect. We've been seeing it with standing waves, but echoes are that way. When you're in a hall that just kind of reverberates a lot, kind of like this, it's just because it's bouncing off of all the material and coming around. If you don't want to have lots of echoes, what do? You put in insulating material to absorb the sound so it can't bounce around a lot. If it all completely absorbs, though, it sounds dead, and it's kind of creepy. So they have to make a balance, and there's people that make careers out of that. You can do high frequencies. Hello!
Luke, I am your father.
But my favorite thing to do is flick it with your finger. The spring. You can set up the vibration directly into the spring. You can see that. Can you see the pulse go back and forth? You can do it as many times as you want. So you can see it and hear it, just to emphasize this echo and back and forth. This works that when you talk, you make the air move. It pushes on this diaphragm and makes it vibrate, which the spring is, of course, attached to, and that sends the waves through the spring. How many of you ever did the tin can with a string thing, like your own makeshift telephone? It really can work. It's this kind of principle. It works better with a spring than it does a string, but I like it. Thank you, Tinny. So if you have a material like a wall and a wave is coming in, and really you can think of it as the wavefronts coming in. The beam, the direction of the wavefronts is perpendicular to that wavefront in every position. So there's one coming over here and there's one coming over here. But let's look at this one in the middle. It's just easier to draw a single line. When it gets here, you know what's going to happen. It bounces off, right? And how is it going to bounce off? Perpendicular to the original direction. That's right. Like that. We call this the normal. Back to with normal force, support force. It's perpendicular to the surface. perpendicular to surface. And with waves, we measure angles with respect to the normal. Not the surface, but to the normal, which is always perpendicular to the surface. So this is the angle that it comes in at. And this is the angle it comes out at. Theta 1 is called the incident. You got the incident wave, the incident angle, the one it comes in at. And theta 2 is the reflected. You got the reflected wave at a certain reflected angle. And for waves, those are always equal. The incident angle is always equal to the reflected angle. So a wave comes into the brick wall over here. It comes off at the same angle it came in at. If you come in more perpendicular to it, it comes out more perpendicular to it. That shouldn't be too far out there for you. So reverberations, acoustics, acoustical engineers have to know all about this type of stuff. They also have to deal with this. We talked about it. I just want to demo it for you. This puts out 1100 hertz. Let's calculate the wave real fast. That'll be a good practice. How do you figure out the size of that wave? The frequency that we just heard was 1100 hertz. What's the wavelength? What do we need to do? Divide it into 1? 1 over the frequency? Gives us what? The period. So that would tell us the time it takes that wave to move up and down, or in and out. This is the rate that it does it. That would be the time it takes for it. How would that get us the wavelength? I want to know the size of the wave. You know, I'm picturing a wave traveling. How big is it? There you go. We could measure the distance that it travels and time how long it takes to get to you. There's an easier way. Divide the frequency by the velocity. Do we know the velocity? It's the velocity of sound. Yeah, it's traveling in air. What's the velocity of sound in air? 340 meters per second. That's how fast the wave is going to travel from the speakers to your ear. So you can hear this time change, this rate change. So, if velocity is wavelength times frequency, the wavelength is the velocity divided by the frequency. That's what we'll do. 340 meters per second divided by 1100 hertz. Remember, a hertz is 1 over second. I didn't bring a calculator. Anybody have that? 0.309. There we go. It's a third of a meter is the wavelength. Let's see. That would look like, let's see, a meter is roughly that. So this is roughly a third. So looks like that. Is that what we're saying? And that's coming from each speaker. Questions about that procedure? But these are in 2 different spots. They're in phase with each other. They're both going in and out. The speakers have to physically move. So they're in phase. If I move it, raise your hand if you heard something change. Most of you. It should have gotten louder and a little quieter. Louder, quieter. That's constructive and destructive interference. It doesn't completely destructively interfere because it echoes and bounces and reflects off the walls and whatnot. And that changes the distance it is to you. But remember we did this on the overhead. Let's look at this one coming to you. It travels this far. This one has to travel a lot farther to get to you. So by the time they get to your ears, they might be in phase, they might be out of phase. If by rotating it, I can change that distance and thus the interference. Some people say it's more conspicuous at half that frequency, so let's go down to 550, and I'll do it one more time for you.
Is there a change for you since you're in the middle?
I do hear something, but because of the echoes. I don't think it's as cool as for you out there, but... Can you hear it? So there's interference, but not complete destructive interference because of the echoes and the reflections of things. Let's just set this down so we don't have to keep worrying if it's in your way. Except it'll be in my way. Okay, we'll do that. Now, waves can also do what we call refraction. That might be a new one for some of you. Reflection, I'm sure you've all heard about. But refraction. There, it changes mediums. That's important. Changes mediums. What do you expect to happen to the wave velocity if it goes from one material into another? Yeah, it would change. So the velocity of the wave changes. It's going to either speed up or slow down, depending on which way it's going. So like air compared to water. As an example. You can go in or out. So let's look at it. You got a wave coming in. You draw the normal. So there's the incident angle that it comes in at. Yes, some of the waves will reflect off the surface at the same angle. So there's your reflected wave. Coming back up. Now, if it traveled the same speed in air as it did in water, it should just keep going straight through like that. But it doesn't. Does it go faster or slower in water? Faster. It'll actually bend then. Let's look at the wavefronts. That one I find helpful. We'll just do them straight, perpendicular along here. Okay, here's you remember those are like the crests, if you will. Crest, trough, crest, trough. All right, this one starts getting into the water. This one right here. How will that wavefront change? What will the wavefront in the water want to do? You just told me. Go faster. And this one will lag behind. Let's show this to you before I finish that drawing. Here's a little board. This is a smooth cardboard, and this is cork, more friction. So here's the rate that this travels down the cardboard. Pretty quick. Down the cork. It's a little slower. I don't know if you can tell. Kind of starts out a little more sluggish than it does over here. So what happens if I let go of it right here? One wheel on one side and one wheel on the other. Yeah, which wheel will go more slowly? This one. This one will be going fast. What will that do to the axle? The wavefront. It'll curve. And watch this. That's refraction. As it changes mediums, part of the wave's in one in medium, the other's the other, and it turns, it bends, it changes direction. And it wants to bend towards the slower side. You can look at it this way. Let's say it's starting out in the fast. Oh, we're going the other way. Yeah, doesn't matter. I'll stay like this. It's going to come in, and it's going to hit her, and it's not going to go straight, it's going to go that way. Did you see it turn? One more time. Comes in straight, and then starts turning, and goes straight in that way. That's refraction. So here, this is going slower than this, so it's actually going to start turning like this. Now it's just getting confusing. I got too many lines up here. I'm trying to make this simple for you. Continue that normal down. It won't go this way. Let's... Once it's in here, it would go straight. But we look at one that's half in there, half in here. This goes faster. I do it the wrong way. This goes faster, so it's going to get ahead of itself. You can see the patterns of the wavefronts. That's how I should do it. If nothing happened, it'd be here. This one gets ahead. It's like it's up here. And this one stays back. Then ahead and back. Can you see they're now like this? It turns. The end result is it comes in, and instead of going straight, it's going to refract that way. I'll draw it cleaner over here. Comes in and refracts that way. So the incident angle is different than this, the refracted angle. Yes?
So like, you stick your hand in an aquarium, and it's got like, your hand it's a few inches over or something.
Yeah, very good. This works for all waves. Everything we've done works for all waves. So with light, you've probably seen this more. Stick a pencil in a cup of water. Stick your hand in the pool, and it looks like it's disjointed or broken or bent. Same idea, because the waves bend or refract, change direction when they change mediums. Starts out in the water, comes out into air. That would go the other way. So see, this was air to water, slower to faster. If you went, well, we can go up. Water, back into the air. Let's say the wave starts out this way. Draw the normal. It would be happy to go that way, but it doesn't. That's how I remember. This one bent. Oh, what am I doing? We measure everything with respect to the normal. My bad. I'm very sorry for messing your notes up. We always measure angles with respect to the normal. Sorry. And I failed. So that one, it got bigger. It went away from the normal. This one will actually go the other way, towards the normal. It'll bend into the water. So it's going fast, 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 and then it slows down and bends towards the normal. This one was going slow, 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 and bends away from the normal. How you remember which way it bends is this. It's slower over here, faster over there, so it's going to curve that way. It's coming in. It's going to curve that way, towards the slow side. That one wasn't as conspicuous. One more. There, we saw it turn. That's refraction. And it works for light and sound. An example with sound. If you had a temperature inversion, say you're across the lake. The author tells a story of, he remembers camping, and they got their tents over here and their tents over there, and they're trying to sleep inside their tent. It's nighttime, And he can hear them across the lake. They're just talking like, well, typical Boy Scouts, I guess, in their tents. They're not yelling, but he can hear them as clear as day. The idea is if you had a temperature inversion where it's cool over the lake and warm up here, okay, going to trap the cool air down here from rising and escaping, then this refraction can happen with sound. If you sit here and shout, "Hello, how you doing?" "I'm doing just fine, thanks." That's about the caliber of Boy Scout conversation. So, the waves are coming out. They're heading up. But what do? They change speed. They were down here at the cool air. They're trying to transition into something that's warmer. They speed up. And the top of this wavefront goes faster than the bottom. Can you see how it would turn? And so even though your sound goes up here, it's going to get refracted and bend back down to here, and you can hear them all the way across the lake. Does anybody ever notice that? If somebody seems far away from you, but you can hear them talking really well? There could be other reasons, but refraction of sound can do that. Okay. Energy in waves. Last thing. Sound energy dissipates to thermal energy. If it needs interactions to be transmitted, those interactions, chemical energy, molecules are moving around, it can heat them up. You send sound through a metal bar over and over and over again, the metal actually warms up because you're making all those molecules vibrate. So which do you think will travel further? High frequencies or low frequencies? Think in terms of energy. Which one's going to make them vibrate a lot more? High frequencies, they're vibrating faster, so it's going to make them jiggle faster. They're going to hit each other more often. And more energy will be dissipated more quickly. So high frequencies can't travel through a medium as far as a low frequency. So your FM and AM radio, FM was in megahertz, millions of hertz, short little waves, vibrating really quickly. They're going to dissipate sooner through the air, the atmosphere, than AM, which is in kilohertz, thousands of hertz. Bigger waves, vibrating less often, less frequently, so they won't have as many interactions, and AM radio can generally go further, be transmitted farther, and picked up farther away than FM. Because of that energy. Energy still has to be conserved. If it's going through something, it still has to make things vibrate. So you can make things vibrate different ways. This ruler, for example, wants to naturally vibrate at this frequency. We could time it and get the frequency and period. It wants to be like that. It's like somebody in a swing. They want to naturally swing at a certain rate, a certain period, a certain frequency, back and forth. So how do you get them to go that big? You have to drive them at the same frequency. You push it. See, notice my push is the same timing as the swing, and it got bigger. It increased the amplitude. What if I push it right now? See how my hand goes back and forth a little faster than the ball wants to swing? Let's exaggerate. It doesn't work. We don't hit what's called resonance. And if I go slower than that, it doesn't work either. You have to drive at the same frequency that it naturally wants to vibrate at. So this one naturally goes up and down about that fast. So if I can go up and down that fast, it gets bigger. Resonance, and the amplitude's larger. Watch if I go faster. It moves, but not as much. And if I go slower, you have to match it. Resonance. I'll do a few more examples next time for resonance for you so we can solidify that. See you Friday.